Consider the curve given by 6xy equals 2 plus y cubed. Show that dy dx is equal to 2y over y squared minus 2x. Find the coordinates of a point on the curve at which the line tangent to the curve is horizontal, or explain why no such point exists. Find the coordinates of a point on the curve at which the line tangent to the curve is vertical, or explain why no such point exists. And part D, a particle is moving along the curve. At the instant when the particle is at the point 1/2 negative 2, its horizontal position is increasing at a rate of dx dt equals 2/3 unit per second. What is the value of dy dt? The rate of change in the vertical direction. First, let's show that dy dx is equal to 2y over y squared minus 2x, and we're going to use implicit differentiation to do this. So, taking our equation and differentiating both sides of this equation with respect to x. On the left-hand side, we'll have to use the product rule, and on the right, the power rule. Now, anytime we differentiate y with respect to x, we will include a dy dx. Differentiating, we get 6y plus 6x dy dx equals 3y squared dy dx. Then we're going to move some things together to collect like terms of dy dx by moving that 6x dy dx to the other side. And grouping those and factoring out a dy dx, we can isolate dy dx and solve for the derivative. 6y over 3y squared minus 6x. And that can be simplified so that dy dx is equal to 2y over y squared minus 2x. Part A done. Next, we'll find the coordinates of a point on the curve at which the tangent line is going to be horizontal if such a point exists. Well, if the tangent line is horizontal, that means the slope of that tangent line is 0. So we're going to let the derivative equal 0 to find if such a point exists. Now, if we let dy dx equal 0, the only way that that can happen is if y is equal to 0. Or in other words, if we set the numerator equal to 0. And if y equals to 0, what does that mean for our equation? Well, plugging y equals 0 into 6xy equals 2 plus y cubed, we get the equation to read 0 equals 2. And that's never true. So we can conclude that no such point exists at which the tangent line is horizontal to the curve. But what about vertical? Part C asks us to find out if such a point exists. And if we have a vertical tangent line, it means the slope is undefined, or the derivative is undefined at that point. And that would be when the denominator of that rational expression is equal to 0. Now we could solve this equation for y and get something a little messy to work with, or we could solve this equation for x and use that to substitute back into the equation. So we get y squared over 2 is equal to x. We'll substitute that back into the original equation to see what it gives us. And with a little cleaning up and simplification, we will arrive that the solution to this equation yields y is equal to the cube root of 1, or 1. And using that to find x, we find x is equal to 1/2. So a point does exist in which there is a vertical tangent line. It's the coordinate point 1/2, 1. And if we look closely at the graph, this would make sense. Here is the point 1/2, 1, and there's our vertical tangent line. Alright, so now we're going to imagine a particle on the trajectory of this curve. A particle is moving along the curve. At the instant when the particle is at the point 1/2 negative 2, its horizontal position is increasing at a rate of dx dt is equal to 2/3 unit per second. Now, what is the value of dy dt means that we need to use the chain rule to find this out. dy dt by definition is dy dx times dx dt. So finding out what dy dx is at this particular point, we just substitute into our derivative, and we get negative 4/3. Now that we have the value of dy dx, and the problem gives us the value of dx dt, we can multiply these two quantities together to get dy dt, the change in the vertical direction with respect to time. And that gives us negative 8/9 units per second. And we can draw the vectors for the dx dt and the dy dt to sort of illustrate what that's looking like at that point. Well, there you have it. That's the last part of this question. I hope you enjoyed it. Please hit that like, subscribe, and notification bell for more videos. Thanks for watching, and stay tuned.